We're going to start. So welcome back, folks, to our second to last Thursday of the semester. Things are winding down. Your next thing that you're in charge of is your last formative assessment, should be number 7. More conceptual practice with interactions. We'll go over that on Tuesday. That is available. Homework 5 is also available due Wednesday night of finals week, so we got some time there as well. Anything that I can help with on either of those activities? Any questions that have come up? I'll just open the floor with that. Doesn't look like it. Well, let us know if you need anything. We have some more stuff to do in Lecture 5 and Example 5. The context of this is that I want to make sure that you know what to do with interaction terms that involve quantitative variables. So in the example that we did in the slides, and this was before break, so if you don't remember this, that's okay. Let me just go back over this a little bit. We filled this in as a group, so this is the filled in version. I had a fake little story problem designed to illustrate why centering matters in fitting interaction terms. And so in this example, we have attitudes on a scale of 1 to 5, education in years, and we have GPA on a scale of 0 to 100. So in this case, if we were to put in main effects, meaning slopes of predictors all by themselves, in addition to a slope for an interaction term, this is slide 7 of lecture 5, by the way, then our reference intercept would be when all of these predictors are 0. So attitude of 0 on a scale of 1 to 5 cannot happen. Education of 0 years theoretically could happen, probably not in a research sample. So right away we know the intercept is predicting something that is not really possible to observe. It's not wrong in the sense that it's going to ruin the model R square or prediction, but it's weird because then you end up with, for instance, negative numbers for an outcome that can only be positive, and you have to explain to people why it happened that way. The same thing, though, happens with respect to the main effect slopes. So beta 1 and beta 2 here. Beta 1 is the slope for how a 1-unit change in attitudes corresponds to a beta 1 sized slope or change in GPA. But that is specific to when the interaction term would drop out, which is when education is 0. So this is a slope that is pertaining to data that we don't have either. Likewise, beta 2 is how GPA changes for a 1-unit change in education, specifically when attitudes is 0, because that's when the interaction term would drop out here, and that can't happen either. So up to this point, 3 of these effects are really not interpretable or useful because they're not describing relationships within people who are in the sample. Either way, though, the interaction term changes the main effect slopes, and in this case, since all the numbers are positive, what it's doing is taking these positive slopes and making them more positive by 1 unit of the moderator. So this kind of language is relatively straightforward. People typically try to make plots then that would show the patterns of these interactions. So you might have prototypical people of attitudes of maybe 1, 3, and 5. You might have a couple different levels of education, and you would create predicted outcomes for these different combinations of people to show the pattern of the interaction. But ultimately, what lines you pick are somewhat arbitrary in the sense that, like, the mean or plus or minus 1 standard deviation to show relatively low versus high, like those are just relative numbers. Like they don't, like someone could pick a different number and it would be just as fine. So one trick in that situation, skipping ahead a little bit, is something called regions of significance to figure out where terms turn on and off. So again, the process that we walked through on Tuesday of how to determine how the model tells you what the slope of a given predictor is at any level of the moderator is start with the slope you want, find all the terms that pertain to that variable. So for instance, if I'm focused on the attitude slope in this problem, I definitely need beta 1 because that's what the attitude slope is to start with. I definitely need the interaction term because it has attitudes in here, but I don't need the main effect of education, and I don't need the intercept because they don't have anything to do with the effect of attitudes. So once you have that, here's the analog for education, only grabbing its main effect and the interaction term. You would then factor out the variable the slope is for, And the components here are your ingredients as to how that slope gives you, how that linear combination gives you the slope for any value of the moderator. So then you can compute, regardless of what level of these predictors you're centered at, what you actually want to happen. You can use this to compute what the attitude slope would be at education of 8 or 10 or 12 or 16 or whatever. So we did some example coding on Tuesday. Here is another example of that. How are folks feeling with filling in the numbers on these things? Feeling okay with it? It's one of those things that it's like really hard at first, but like once it clicks, like then you have it. And you just have to like be patient to get to the click. That's the harder part. So in this case, we give a 1 to the spot that holds the main effect of the predictor whose slope we're trying to find. And we give the value of the moderator in the spot of the interaction term for who we want that slope for with respect to the other variable. So here's a different one. We can try to fill in these values. Let me get out of the presentation so I can do that. Slide 13 is where I'm at. So here's another one. Let's say that this is my model. I have age, I have binary gender in which 0 is the men, 1 is the women, and I have their interaction. Let's say that we're predicting some outcome here. So what would be the ingredients I need to get the age slope for either gender? What would I need? I need beta 1, for sure, because that's what the age slope is. That's a good place to start. What else do I need?
Beta 3 times woman, or gender.
Yep, yeah, whatever you want to call it. I name it this because it's like, I name it by what the 1 means, usually. So like this is the effect of turning this on for this type of person. Make this back here. I got the dreaded, your internet is unstable message, so I'm trying to type extra slow. I know, right? And I'm on campus. Come on. If the internet isn't good here, I don't know where else to go. But yes, it would look like this. That's the ingredients for how you would get the age slope. So for instance, down here I have Stata code. Our code would look very similar. If I wanted the age slope for men, what would go here? A 1. What would go here for the main effect of gender? Do we need it? Nope. Age slope isn't in there, that's a 0. And what goes here if I want the age slope for men? Yeah, given the coding scheme. It is 0, indeed. If I want the age slope for women, what goes here? A 1. What goes here? Ooh, 1 or 0. We got 2 conflicting answers.
0, because that's the main effect for gender.
That's right. This is the thing that folks screw up when they're first learning this. The inclination is to be like, well, it's for a woman, so I need to turn this on. But no, this is the gender difference irrespective of age. What we need to turn on is the interaction term for how the age slope differs in women. So the 1 goes in the interaction spot, not the main effect spot. Now if we go the other way, what if I want the gender slope? What are my ingredients?
Beta 2.
I need beta 2 at a minimum, because that is where the gender slope starts. What else do I need?
Beta 3 times age.
Beta 3 times age, because we've already factored out the gender spot. Here we go. So now if I use this as the ingredients for how I get a gender slope, what would it be at age 80? What goes here? If I want the gender slope for an 80-year-old, what goes here multiplying the main effective age? 1 vote for -5, 1 vote for 0. In this case, it is still 0, because the main effective age has nothing to do with the gender slope. You gotta refuse the urge to put the moderator values in the main effect spots. But what we do want is a 1 here, because the gender slope is what we want. And if we want it for an 80-year-old, then the -5 goes at the end, -6. There we go. Likewise, if we wanted it for a 90-year-old, the main effective age is irrelevant. The gender slope is what we need to start with, and then we fill in the value of the moderator that we want the gender slope for. So at this point, you see potentially an issue with what you get back. Like, for this version of the slope, when we're focused on the effective age, in this data set, given the model, there are only 2 possibilities. Because age is interacting with a binary variable, we have an age slope for the 0 group or the 1 group. The end. End of list. But the opposite is not true. If I want to know about gender differences as a function of age, every unique value of age has a different gender slope associated with it. So it would be just as useful potentially to plot 75 as 76 as 79 as 80 as 82. And it's like, okay, then what good does that do to pick arbitrary numbers? What we might want to know instead is the age at which gender differences start to matter and the age at which they no longer matter. Because the slope is going to get more positive as the moderator goes up or less positive, right? At some point, it's going to go to 0, and at some point, it's going to go in the opposite direction. So finding the boundaries at which a simple slope turns on or off can be much more useful for quantitative variables that are moderators. So I want to show you how to do that. This is slide 14. This technique goes by a bunch of different names. I learned it as regions of significance. In R, there's a package called like Johnson-Neyman or something, because this idea was stolen from a paper from like the 1930s. Like they took that technology that was invented then and leveraged it for this purpose. So the idea is that if I can figure out what the t-value is where significance starts, and this is ignoring degrees of freedom essentially, where we're talking about 1.96, right? I can just reverse engineer the equation because I know that estimate over standard error is t. I just need to figure out what the estimate needs to be to get to where t is 2. So I rearrange and I solve for that. And it ends up being a term that is quite complicated, but it tells you essentially where t hits significance and stops on each side of it. So let me show you an example using these particular data. And this is something that you can do. I have an Excel worksheet that does this. There's R packages. I wrote a SAS macro. Hillary, do you know, does Stata have any routines that do this? I couldn't find any, but I may have just been looking in the wrong spot. Exactly. Yeah, so Stata users, by the way, Stata packages work the same way as they do in R. Like people make packages to do specific things that you can then download and install into Stata. They're user-defined packages. The extension is usually .ado, and I'm not sure why that's different from do, but it is. So I found a bunch of useful stuff just asking the Google, like, does Stata have a package that does this? And it says, search for this, and then I can find it. So regions of significance, simple slopes, or Johnson-Neyman, those are the search terms I would start with. But let's say here's my equation. Let's say beta 2 is minus 0.53. So at age 85, there is a gender difference favoring men such that women are lower by 0.53 in this example. And the interaction term is negative 0.11. So this is a more negative pattern. Essentially, the age slope is becoming stronger, the gender slope is becoming stronger as people get older. So if you feed this information, essentially, what is the coefficient for the main effects and the interaction? What are their standard errors? And then there's one more piece that I'll teach you how to find, which is a covariance among the fixed effect estimates. Then you can feed these things into calculators or functions and figure out what the boundaries are. So the end result of this found 2 ages, essentially, where the gender effect is predicted to be significantly negative above age 79, non-significant between 79 down to 60, and then significantly positive below that. So then the question is, how are these variables distributed in your sample, and for how much of your sample would you expect this effect to be significantly positive, non-significant, or significantly negative? So I'll show you how to do those kinds of things in practice. So, how are we doing so far, folks? Quantitative by quantitative interaction terms. There are still examples out in the world of how not to do this. So let me give you an alternative that I still see sometimes. I have two numeric variables that interact, and I want to figure out how to explain their interaction. I'm going to cut them into thirds. I'm going to make arbitrary categories of low, medium, and high. That way I can get the slope for the low group, for the median group, and for the high group in either direction. What do we think of that idea? Taking a continuous variable and cutting it up into 2 or 3 categories. We have 1 vote for definitely no, 2 thumbs down.
Super.
That's a super no. Super duper no. Hillary, what do you think? Yeah. See, the reason that folks do this, they cut things up, is because they're used to thinking about the world in this kind of way. Like, this is the slope in this group, this is the slope in that group, and it's all neat and tidy. But if you take a numeric variable and you cut it up into categories, you're introducing measurement error on purpose. Let's say that you have a 1 to 10 scale, and you decide that 1 to 5 is going to be the low group and 6 to 10 is going to be the high group. Well, then you're saying that the 5s and the 6s are just as different from each other as the 1s and the 10s are. That seems kind of not cool to me. And actually, not just me, there's a whole literature on this that says, yeah, bad, don't do it, and has math and simulations to prove it. So I want you to not have to cut up continuous variables. I want you to know how to treat them in their original forms. So none of what follows is needed for homework 5, but here's an example of how you would go about this. So I'm picking up on page 7 of example 5. Up to this point, we had fit a main effects model in which we examined the unique contributions of age and grip strength as linear slopes, differences between women and men and among dementia groups, and we had previously considered sex differences and the effect of age and grip, did not find any, took those terms out of the model, and now I'm considering an alternative interaction, which is, does the effect of age vary by grip strength, or alternatively, does the effect of grip strength vary by age? So we can agree that being strong is good for you, right?
So do both of those have to be true
Yeah.
for it to be significant? Okay, yeah.
Yeah, so the interaction term mathematically applies either way.
Okay.
How you talk about it is a preference. And to avoid confusing people, I usually go one way and not the other, but there may be situations in which you want to talk about both.
Okay.
But it is true that if the effect of age varies by grip, then the effect of grip varies by age too.
So in a paper, what I hear you saying is you don't have to address both directions.
That is correct.
Necessarily. Okay.
Yes, and I think that it depends on the story, because usually there's like a focal predictor and then there's a series of moderators, and that's how people think about it. Like, here's the slope I care about. Is it stronger for these people than those people? Is it stronger at this occasion than that occasion? So that is usually sort of set up as the research question. But absent of that, then you could pick one, whichever is easier or more interesting to you. But yes, like in this case, being strong is good for you. We had a main effect of grip strength that was positive in predicting cognition, such that folks who could squeeze more pounds on the stress test had higher cognitive scores. And that's where I make a joke that says, if you want to get smarter, go to the gym. But the point I'm trying to make is that this is not a causal inference situation. There's lots of things that would co-occur that would cause cognition and physical health challenges, especially as a function of age and increasing probability of disease. Likewise, aging is bad for you. I know, like, spoiler alert, guys. Buckle up. Your 40s are going to be a rough ride. I'm just going to put that out there. Yeah. The 30s were I was not a parent for most of my 30s, and so I think my 30s were probably a little bit different as a consequence of that. But yes, buckle up. Aging is going to be quite the ride. Middle life is especially quite the ride. So aging is related to lower cognition. But can you fix it? Like, are there ways that you can mitigate the deleterious effects of aging, such as through strength training, right? That's a thing that people want to know. So that's, and if I were to spin it that way, I would focus on how do we fix aging being bad for you? Like, are there things that moderate that such that aging is less bad for you in certain kinds of people with certain kinds of habits and that kind of thing? So it just depends on the story. But what we're not going to do is cut these things up. We're going to keep them in the form that they are because we don't want to artificially introduce measurement error in age or grip. So, with me so far? Okay. Then syntax and output. So I have stated first as usual. This new model has an interaction term that is significant, so we will keep it, we will talk about it. The overall model itself remains significant. And do I know from just this screen right here if the change in R square relative to the main effects model is significant? Is there anything on this screen right now that tells me that without having to do additional work? So I'm comparing in my head the model with only main effects to the current version that includes one additional interaction term. Do I know from this page if that additional interaction term significantly increased my R square? Yes, no question. A finger. I don't know what finger means.
Pointing up.
You're
Or,
thinking
oh,
up?
maybe the thumb up.
Thumb up. So we do know? You think we know? Okay.
That'll be my vote.
That's fair. Do we know? And if so, how? Follow up. More generally, if you have a model and you add one thing to it, and that one thing is significant, yeah, that means the change in the R score, the one thing created, is significant. It's a one-to-one correspondence. Where we have to do extra work is if you add two things at once or three things at once. Then you don't know what their joint contribution is together because that has to include their shared variance. So in the previous analysis, we added two interaction terms at the same time. That requires a separate hypothesis test of those two slopes to see if their change in R square is significant together. If there's only one, then we know that it is. So I can look at the output for this model, 0.2894, and compare it to the main effects model, and the difference in R square must be significant because this slope is significant. Now, what does it mean?
Subtract those,
Mhm.
is that the whatever for this term then?
Yes. The difference in the R squares between this model and the one without the interaction term would directly tell you the change in R square. That is also semi-partial R square for the interaction. It's one and the same. Yep, it's the amount of the R square this term is responsible for. So let's walk through. My constant is 29. That is still for an 85-year-old with 9 pounds of grip who's a dude who's not going to get dementia. Because we've added an interaction term among existing variables, so we don't have to further condition the intercept on anything new. Now let's go through the list. Which of these are marginal and which of these are conditional? Okay, age slope, marginal or conditional? For everybody or only for some people? Yeah, so this is preparing you for homework 5. I have marginal, unconditional as one choice. I have conditional or simple as another choice, I think. C for conditional, this way. Got 1 vote for C. 2 votes for C. Now the question is why?
Because there's an interaction.
Because it's right there. Yep. If you see the variable listed more than once, it's conditional. Because that means these terms both work together to describe how the main effect of age functions. So this one has to be specific to when its interacting variables are 0. So putting it together For people of 9 pounds of grip strength, near the mean of the sample, for every year older they are, cognition declines by about 1/3 of a point on this measure. In people of average strength. Likewise, grip 9, marginal or conditional? Conditional, same reason. How about gender? Yeah, marginal, marginal, marginal. You only see them once. That means this is the gender difference in cognition, period. It's after controlling for age and grip, but it's not specific to anybody. These are how bad dementia is for you, period. Okay, so for grip strength then, for every pound older I am, nope, not even close. I told you the 40s were rough. For every pound older I am, that's excellent.
You know, for some people.
For every something goes up by 0.6. There we go. Right? That's where I'm at. And honestly, like as a methodologist, that's what it is in my head. Like people tell me their variables, and I'm just like, what's X, what's Y? I don't remember. Like for every something, but your readers will care. So let's get this right. For every more pound of grip strength I can do, cognition is higher by 0.6 if you're 85 for people of average age. There we go. So which way do you want to go with the interaction term? Who's going to be the moderator first? Any preferences? No, we don't care? All right, we'll go with age. Age is my story. Grip strength is my moderator. So age is bad for you in people who are of medium strength. What happens to the age slope in stronger people? The age slope is negative, the interaction with grip strength is positive.
It gets less bad.
Less bad, exactly. Yes, negative and positive means it's less something, means it's a weakening. Age has a negative slope that becomes less negative by 0.12. That's the interaction slope by 0.12 per pound of grip strength. So every slope is always in a unit. In this case, it's the unit of the moderator. So the age slope is negative. The moderator makes that age slope less negative by 0.12 per unit grip, which is a pound here. Yeah. So age is less bad. And I once had someone argue with me over this less negative, more positive distinction because it's heading in the same direction on the number line. Because eventually, what's going to happen to the age slope?
Flip over.
Yeah, it's going to flip over to positive. So in that sense, less negative into more positive is heading in the same direction. Likewise, less positive into more negative is heading in the same direction. And the student was arguing with me about calling these different things. And I will point out as precedent the Weather Channel. I grew up with the Weather Channel and cable. I think it still exists somewhere, but most of us just look at our phones and stuff. But in the wintertime, they say language like, not as cold, right? That is less negative. And in the summer, they say not as hot. The Weather Channel is not going to lie to you and say, oh, it's going to be warmer tomorrow. And by warmer, I mean from -20 to -10. Like, that's not warmer, that's less cold. So, yes, for instance, I spoke with my new department chair this morning. We were complaining about the Iowa weather because it was -6 during this conversation. And she's like, yeah, it was really chilly here today. It was 40. I'm like,
Oh, I will
Hold
vouch.
on to the response, like, don't flip them off like you're impulse.
yeah,
might be
exactly. I'm
like,
like, yes, 40 is definitely chilly.
I will vouch after living in Yuma, Arizona, which I call the armpit of the United States. It's so hot.
Arizona,
And
yes.
it's always white. There's like no color, it's just white. When I came back and it was like 40 degrees here, we were already like, at a temperature, and then 70 degrees was like,
Mm-hmm.
I mean, it's weird, but yeah, your
Yeah.
body adjusts to.
Yeah, no, I'll go running in shorts in 40 degrees, right? That's not chilly, right? That's fine.
Not for long.
Not for long.
Depends what you're used to.
Yeah, it also reminds me when I moved to, so I was a postdoc at Penn State in Happy Valley, Pennsylvania. They don't really have summer there. Like, I barely ran my air conditioner. And I remember the weather forecaster saying that the next day was going to be oppressively hot. Oppressively 88. That was the forecast. It's like, nothing. So, yeah, it's all in the eye of the beholder. But I think saying age is less bad for you is a more intuitive way of thinking about it. Because you have to encode that a negative slope is a bad thing, because this is an outcome where we want higher values, we want better cognition ideally, and to make the slope less negative means to bring the bad effect down. You want to go the other way? Now we have grip strength. Age is now the moderator, so grip strength is good for you. What happens if you're old?
More good.
More gooder, exactly. So it matters more if you're strong, if you're also old. I might not say more gooder in a paper, but you get my drift. Less worser, more gooder, that kind of thing. So I went through and computed some stuff to show you how to do these sorts of things, because this is something you may want to do. And I also wanted to throw in some shortcuts for folks. Since now you've done the algorithmic work to like figure out how to do things, it's time to show you the shortcuts so you don't get too irritated in practice of doing the same kinds of things over and over. So this is the simple age slope. If we pull all the terms out of the model that have age so we can figure it out, this is the core ingredient that we need right here. And so then these three Lincom statements, for instance, provide the age slope at values of real grip strength of 6, 9, and 12, accomplished as -3, 0, and 3 in the centered variable. These three lines can be replaced by this one command. And actually, this command could generate thousands of lines of code if you wanted to, because it's rolling through a list. So what's happening here? This is a command called margins in Stata, which does like 8,000 different things. So there's not like a one-size-fits-all to this. But this use case says, for a range starting at -3 in increments of 3 up to 3. So I just picked 3 values for demonstration purposes. I could have fed in every unique value in the data set if I wanted to and had it loop over all of these things. And then what am I asking for? The dydx of age, which is why I brought this up on Tuesday. That stands for derivative. So we're asking for the first derivative with respect to age at each of these levels of grip strength. So the moderator goes in the at thing right here, what you're looping over. The variable you want the slope for goes in the dydx. So here are the results for these prototypical values of roughly -1 standard deviation, the mean, and +1 standard deviation. So if I look through the list here, at the first one, that's at -3. And note, I hate this data does this. Hillary, do you know how to fix this? Like, it just lists them in order, but it doesn't tie it to what you said up above. So I find that annoying. No, we don't know how to fix it? Okay, well, it's just going to be a pain point then. That's fine. So this is the age slope at a grip strength of 6, and it is significantly negative. Yeah, so age is worser for you if you're weak. That's what this is saying. Number 2 is the one we got out of the model already, because that is specific to a grip strength of 0, and we'll see that that's significant. Number 3 is the age slope at a grip strength of 12. And not only is it not significant, it's flipped over, right? And that's to be expected, because you're starting out negative this way, and you're just gradually becoming less and less negative. Eventually, you're going to head the other way. But then this begs the question, so how strong do I have to be before age isn't bad for me anymore? It's still bad, it's still bad. Oh, not bad anymore. So somewhere between 9 and 12 is where age stops being bad for you. But then if I follow my arm logic past, at some point, if you keep going, weaker and weaker and weaker, age starts being good for you. So there's another point where you're going to flip over again. So regions of significance is trying to figure out where these flip over points are and tell you exactly what those moderator values should be. If I go the other way, I run into the same kind of issue. So this is simple slopes for grip strength at prototypical values of age of 80, 85, and 90. So now the terms in the margins have traded places because the moderator is age, and I want to start at -5, which would get from 85 to 80, in increments of 5 and go up to 5, and I want the slope for grip strength. So now, we said grip strength was good for you, right? And it's more gooder if you're older. So this is the middle one. This is what was in the model. This is at age 85, good for you. Well, since we expect the interaction pattern to strengthen it as the moderator goes up to 90, even more gooder for you. But somewhere between 85 and 80, the slope shuts off. So grip strength doesn't matter somewhere between 80 and 85. We got to figure out where that boundary is here. And your reader is going to be like, oh my God, can I please have a picture already? And so you shall give them one. But you shall not give them this picture. So this is just, I ran this code. So margins now is being used to generate predicted values. So to make this plot, I am holding constant gender and dementia. So I would say these are predictions specifically for a man who's not going to get dementia. And that's okay because those variables don't interact with either age or grip. So changing the reference to be a woman who is going to get dementia, for instance, would shift the whole plot up or down, but it wouldn't change how the lines differ from each other. So you just got to hold everything else constant. And I created 9 predictions, essentially by looping over these two things. And then I saved these 2 plots as image files. Now let's talk about briefly, why do these plots suck? I heard somebody. Maybe I'm hallucinating.
I coughed.
You coughed? Okay.
I coughed.
Well,
What
first,
is linear prediction?
yeah, what's my y-axis? Linear prediction. No. I mean, that's technically correct, but your reader's going to be like, linear prediction of what? So,
Same with the title. Title just says
adjusted predictions. Oh, super. Yeah, so I would edit the y-axis to be predicted cognition, probably, and I would use predicted in there so it's not the real data. It's what the model says. Also, what do we think about the scale of the y-axis? 20 to 35. The scale of this outcome, I think, is 0 to 40 something. So I might want to blow that back out a little bit, like it's kind of zoomed in a way that seems disingenuous potentially.
Unless there's a reason that 20 is like significant.
Yeah, like if 20 is some kind of threshold or something that people would care about, then maybe having it within this range would make sense. But generally speaking, you want your y-axis to show like the range of the full variable. What about the x-axis? What do we think of that?
I would change it to reflect what the actual
Yeah,
measurement would be.
don't make the reader do the centering in their head. That would be my advice to you. Just put the original variable on there, even though the predictions are from the centered version, just plot with a different x. And age 85, that is the name of the variable in the data set. That does not go in a plot. So you would want to rename that so that it's like age, something that looks nicer like that. And then the title, yeah, I would fix the title. I do like the error bars. I do like the colors. Journals nowadays are much more tolerant of using color, but that would be something to check ahead of time. Whatever journal you're targeting, do they allow color? If not, know that from the beginning so you don't have to redo all your plots. That was, by the way, what hung up my dissertation. So I'm in thesis and dissertation deposit land right now. They're all due on Monday. And mine was kicked back because I had color and they didn't want it. So the compromise was that I manually printed color sheets and inserted them into the black and white dissertation, and then they were okay with it. Yeah, I know. That was back when you had to make it, pay for it to be a book. I have like dissertation books. Yeah, I'm glad that we don't do that anymore. Because it was also custom to order a book for each of your committee members, And these bound dissertations cost like $85 a piece. So it was like an investment to give your faculty member a hard copy of your dissertation that they're probably gonna just toss.
I'm gonna say, let's go put it in a big pile of.
Yeah. So anywho, check to see if they allow color. But yes, readable axes in the scale of the original data is gonna help your reader understand what's going on. But that being said, in terms of what we know, the red dot in the middle here is like the anchor point of the model for the intercept, because this is 0 with respect to grip and 0 with respect to age. So that's my intercept. The slope of the red line tells me what the main effective grip is according to the model, because that is where the moderator is at 0. We know that each of these lines, the green line is significant and the blue line is not. So we're sort of looking for the point where this turns on and off. Like this one over here, this is the effective age being bad for you. So this is the anchor point, the middle dot here. And the slope of the age line is the main effect that's given by the model at grip of 0. And we can see that age is bad for you and it gets less bad for you. So somewhere between, it was green and red, I think, is where age starts being bad for you. And then if you go up, eventually age is going to start being good for you. So we want to figure out what the boundary areas are that make these plots make sense. How to do that? Here is a new vocabulary word. Asymptotic covariance matrix. It's a fun one. This is a covariance matrix, meaning that what is on the diagonal, so all covariance matrices are structured the same way. On the diagonal, these values right here, for instance, these are variances of some kind. And what's on the off diagonals are covariances. So you remember what variance is, right? It's like how spread out things are. And covariance is how things go together. So you learned it as correlation in a standardized format. But it's like if you're above the mean on X, are you above the mean on Y? And covariance is in the units of those variables. Correlation is the standardized version. This particular covariance matrix has nothing to do with your variables. This has to do with the uncertainty and what the fixed effects should be. So the covariance that is needed to compute regions of significance, I've highlighted the ones here, are among the slopes out of your model. So this is a piece of output that you would usually completely ignore. It's not default. You have to go and ask for it. So in Stata, there's a command. SStat means give me something after the model's done running. VCE, I don't know what that stands for, but it gives this table. So we need, on the diagonals in this case, are the standard errors squared for each of the variables, and then the covariances among the standard errors are in these off diagonals. So these are values that if you don't have a built-in function in Stata or R to use someone else's spreadsheet or calculator, you'd have to go find these things. And I did compute the boundaries based on this, and here is code that would show what happens. So these are the boundary ages for, boundary values for grip at which the age slope turns on and off according to the output that I got from this process, and these are the boundaries at grip strength as well. So if you run this output, you'll see that P is exactly 0.05 for these things, because that's where things switch on and off based on significance. Now, our folks, I will show you the same process unless there are questions from the Stata folks first. No. Hillary, did you get to sleep in today?
No,
You did not?
no.
No.
My youngest wakes up at like 7 o'clock every day, no matter what.
That's unfortunate.
You know, I mean, I'm thankful it's not 6, I guess.
Yeah.
But like,
I swear last night I felt like a kid, like, getting my own school canceled because we get the note from the school district that it's a 2-hour late start. And I'm like they decided it now as opposed to 5:30 in the morning where I have to wake up to find out that I didn't have to wake up. That's the worst.
that's always.
Oh, no, I get notifications, I get texts, I get emails, and I get phone calls. Like when they announce something, it goes like through all the modalities, so you can't miss it. But I was just so happy they decided it last night.
Yeah.
So maybe you got a half hour extra or something.
I mean, I had more like quiet time.
Oh, there is that.
And I will take that.
Yeah, quiet time.
Back
Exactly.
in my day, we had to watch the TV.
I
You didn't
know,
even
back
get
in
phone
my day,
calls.
you had to
You had to
watch the
wait
TV
for
and
it to scroll
wait for
by.
the bottom
And
scroll.
if you missed yours, potentially you'd wait for it to
Yeah.
recycle.
Yeah, or the radio station. They would read the long list of schools that are closed, and you're just sitting there waiting because you know it's in alphabetical order. It's like, come on, come on, come on. But as a child, I didn't mind that I had to get up early to find out that I could have slept in because I was not going to sleep in either. But it's a different story. My kid, of course, wanted to still be woken up at 6:30 so he could get in as much video games before school as humanly possible. Like, yeah, same. It's about Brawl Stars. Can anyone weigh in on this?
It's like a fighting game where it's like Super Smash Bros. In a way.
He loves Super Smash Brothers. That one I'm familiar with. But yeah, it's all about Brawl Stars right now. So
Does he like the movies too? Because there's a new Mario movie coming out.
I'm not sure. He's not much of a movie kid. Like that's a lot to ask him to sit still for like 2 hours or an hour and a half. You know, that's not so much. But he will sit and play this game, you know, until his iPad battery dies. Like that's what. But he's outsmarted us because now he started sticking charging cables like all over the house where he wants to sit. So he just moves to a different chair.
Oh my gosh.
Yeah, yeah, yeah. But no sleeping in tomorrow. Hopefully, we'll get above 0. Hey, it's at 16 now. Not as cold. Not as cold. That's what it is. It's 16 degrees right now. So in our, let's see here, we're adding the same interaction. We're coming to the same conclusions regarding the model being significant. The same story is true with respect to if the interaction is significant, that means that the change in the R square it created is necessarily significant. There's one term that's doing the work. I created a function to compute the change in R square explicitly, so you don't have to do that with your calculator. So the addition to the R square is 0.01. Not a whole lot, but not nothing. So in R, I'm going to show you a couple different ways to get simple slopes. This is the annoying way. Can we agree on that? I think we can agree on that. R will automatically reorder your terms to put interactions last. So just keep that in mind. No matter how you write your code, you need to check the order of this table to know what the order is of these terms. But what I'm doing in the first pass is computing age slopes at levels of grip as the moderator. So the ones go in the spot where the age slope is. The moderator values go in the interaction spot to turn the age slope up or down as a function of grip strength. Likewise, these are the grip strength slopes, so the main effect of grip is turned on as a 1. The interaction term now takes the value of the moderator with respect to age. So different values in here because in one set the moderator is grip, in the second set the moderator is age. So here is the results from that in terms of somewhere between, this one. Somewhere between grip 9 and 12 is when age becomes bad for you, or stops being bad for you rather. And then somewhere between 80 and 85 is where grip strength starts helping you. I found this package, Reg Helper, has a function called simple slopes. That seems nice. After a little bit of trial and error, I got it to do what I wanted. So I'm listing for the age slope. This one is giving me age as the moderator. This one is giving me grip as the moderator. And I don't remember what SS test means, but I needed it to make it work. So we get the same 3 slopes out of 1 line of code, 6 slopes in total out of 1 line of code. I also used prediction as a package and a function by the same name that makes code that looks a lot like Stata with respect to how you generate predicted values. So those of you who are doing homework, note that any variable that is not being looped over, so in this case we're looping over grip strength and age, you need to hold constant explicitly. Otherwise, if you don't set these to 0, it fills in the mean, and that's not the same thing. In particular, like the mean age would not make, or the mean gender would not make any sense here. Like you're either a 0 or a 1 as stored in the data. If I filled in like 0.6, it's like, who is that for? Yeah, it's odd. And in so doing, I got this error message. in check values data at value for 85 is outside the observed range. So this is yelling at me that one of my combinations is outside the range of the data. Like I don't have a full crossing of low and high of age and grip, but that's okay. I can live with that for the purposes of making a picture. And the code to make the pictures is online because it's kind of ugly, but here's the same patterns. So I had a little more control over this in terms of the axes and stuff because I had to do a lot more coding to get these pictures, but it's the same thing. So in R, vcov is the function that generates the asymptotic covariance matrix. So it's set up the same way as in Stata, and I've highlighted the numbers that you would need to compute the boundaries. By the way, you don't have to do this in homework 5, but I did want you to show it to you. I found a function called Johnson-Neyman that will provide the boundaries at which the simple effects turn on and off as a function of the moderator. So this is the output that I got. When grip is outside this interval, the slope of age is p less than 0.05, and then they note the observed range of grip in the centered one. So the first thing I did was translate this into the original variable. It was centered at 9, so I had to put 9 back into those things. And so then I can put it together. The result indicates the age slope will be significantly negative below a grip of 9. So if you're on the weaker side, age is bad for you. It is non-significant between 9 and 18, and then it flips to be positive after 18. So let's look at the plot with respect to that. So here's age. So we figured out that a grip that is 9, what is it? I just lost it. Significantly negative below 9.6. So this red line here is right at 9. So just above it, any moderator value that is lower than that is going to have a negative age slope. But if you follow up past green, what's going to happen if I kept going? Flips up to positive. So then it says where it flips to positive is after 18 pounds. Well, in this sample, I don't think anyone had 18 pounds. So in chapter 2 of my book that's on your reading list, I tried to walk through the logic of this. You would first want to figure out, like, for what proportion of your sample you would actually have a positive slope, a non-significant slope, and a negative slope, and then use that to try and interpret this. So in this case, we're going to have, I think, about half the folks who have a negative age slope given their grip strength. And then the other half, it's going to be non-significant, but there's not going to be anybody who has a positive age slope because grip strength doesn't go that high. So we wouldn't need to worry about that upper boundary in practice. Likewise, if I flip it, which is the predictor, which is the moderator, then it computes the interval, and I got to add 85 to get back to the original version of the variable. We find out that the grip strength slope is significantly negative below 70, non-significant between 70 and 82.7, and then positive after 82. So grip strength is bad for you if you're really young. It doesn't help between 70 and 82, and it does help after 82. So that solves then the question of at what point does this turn on? It turns on at 82. So those are regions of significance, and then here's the output just demonstrating that it works. So the program then renders the values where P is 0.05. So we have, these are the two for age, and these are the two for grip. And then I have a very extended results section right here. All right, how are we doing, folks? Okay-ish? When would you do this in life? That's all I want you to hang on to. The rest of this you can come back to and read it again.
Can you have an interaction term of two quantitative?
Yes, when you have an interaction term involving at least one quantitative variable, quantitative predictor, you would want to find the points on that where the other slope turns on and off, as opposed to just this one, that one, this one. That's when this would be useful. Hang on to that, and then you can come back to this as needed. So in terms of a write-up, here we go. I'm picking up on the text that I wrote for the main effects model That was in example 4B. And then going through line by line to interpret the results of this right here. Or that's the wrong table. These results. So I am describing this algorithmically, but what is not in any of these results sections is the context. So this gets to your question about like which is the moderator and can you pick? Like I'm just laying out like this means this, this means this, this means this. What you would need to add to make this work for a real paper is, as stated in research hypothesis 1, we found this result. Like you got to tie it to what your questions or hypotheses were to begin with. That way your reader's like, why are you telling me this? Oh, it's the answer to this question, and how does it answer the question? So I can't anticipate what those sorts of additions would necessarily look like. I can just warn you that they need to be there as framing for why the reader should continue reading. In this case. Yeah. Wow, we're already at the last model. Very cool. Let's see. Do I want to do anything more in here? I think I could. No. Actually, yes. Can I do 2 slides and we'll call it a day? Can we agree? I'm still letting you out early. 2 slides, because this is going to set up for next time. Next week, in fact. Slide 16. When there's more than one interaction. So we did this in the last formative assessment when we had like F interact with 2 things as a predictor. So just to try and lay out the logic more formally. In this example, I've got some generic labels for my variables, W, X, and Z. I have an interaction between X and Z and W and Z. So then if I go through the conditionality of this, all of these main effects are conditional on something because they're all part of an interaction term. So I got to look through the list and say, okay, here's W. The only other spot that I see it in is this interaction, so that means that this W slope beta 1 is specific to when Z is 0. It's not conditional on when X is 0 because it doesn't interact with X. Likewise, X only interacts with Z, therefore beta 2 is specific to when Z is 0 for the same reason, but Z interacts with both X and W. So because it interacts with both, it's conditional on both. Cough, cough, homework question. There's drop-down menus for this. The slopes are only conditional on variables they interact with. If they don't interact with it, they're not conditional. Question?
If this was a real situation, you found out that those were significant interactions, would you also want to see there's an interaction between X and W?
Yeah, unless there's some reason.
This is your starting point.
Yeah, like I'm sort of assuming like this is where you landed for whatever reason, but yeah, I think if absent theory or any other reason not to, I don't see why you wouldn't want to explore potential interactions. And potentially a 3-way, like for that too as well. And that's like later in the slide deck though, because this is enough. Yeah. But the interaction slopes here, we would use the label unique marginal because they do not get moderated by anything else. So we can talk about beta 4 either way correctly. It is how X is moderated by Z or how Z is moderated by X. And beta 5 is the same way. We can talk about how W is moderated by Z or we can talk about how Z is moderated by W. Either one of those things is correct. So why would we need to do this? In situations in which we have categorical predictors. So for instance, in your golf homework, remember that one? Yeah. I have 4 golf groups. What if I wanted to ascertain whether the effect of golf training varied by enthusiasm for mini golf? Could I do that? Is some kinds of training more effective in people with more enthusiasm than less? Could be. So I have 4 golf groups, right? How many slopes does that take to differentiate them? 3. So if I want to know if golf training type interacts with enthusiasm, how many interaction terms do I need? Keep on camera. 3. Because each of the contrasts that differentiates an alternative group from the reference would need to interact with enthusiasm. So you may have to add multiple interaction terms at the same time to fully capture all of the interaction pattern that you want. So that's the last example that I have is with dementia group so that you can see what that would look like. Yep. So this would be the ingredients for understanding what the simple slope of each of these variables would be for any value of their moderator. So for W, I only need to know what Z is. For X, I only need to know what Z is. But if I want to get the slope of Z, I have to fill in values for both X and W because it interacts with that. Yep. So, all right, we'll do the rest of that later. I think that's all I want to say about that. So here is what I told you the other day, just in case you didn't, if you want to have that in writing. I am showing you manual coding processes so that you understand what is happening. Once you understand that and want to take shortcuts in terms of the efficiency of your syntax, in IDOT and Stata, any categorical variable will have its dummy codes made for you. If you designate it as a factor variable in R, the same thing happens. This is analogous to the by statement in SPSS instead of the with statement in SPSS syntax, or the class statement in SAS. So that is an option for making things a little bit simpler. It has some cost to it, which is why I decided not to go into it, but there is another way to make your code a little bit more efficient. There. We will see that next time. Interaction terms involving grouping variables. All right, 305. Any questions or things you want to hear repeated or differently?
Say that, why the bit 4 and bit 5 is
Why is that the case? Because X moderates Z and W moderates Z to the same extent for everybody. So these interaction terms would be considered marginal because they're not conditional on anything else in the model that they are embedded within. So I think I can answer this better if I do fast forward to three-way interaction slide. Yep. So three-way interactions, for instance. In this case, like if I had something that looked like this, I have three main effects. I have all possible two-way interactions among them, and then I have a three-way. So in this model, beta 4 is specific to when W is 0, because it's also X and Z together are embedded here. So in this case, beta 4 is conditional, because this is how X moderates Z specifically when W is 0. It does so differently as W increases. Does that help? Maybe not yet. Basically, what you have to ask yourself is the term that she's asking about, do I see that embedded in anything else in the model? If the answer is no, it's marginal. If that term is embedded in something else, then it has to be conditional, because it's whenever the something else is 0. So if you're focusing on the interaction, it's not just X and Z separate, it's their unique combination. Like literally, if you made a new column in your data set that is X times Z and thought of that as a separate variable, then its effect in this model with a three-way interaction is conditional when W is 0. Without this three-way interaction, it would be unconditional though, because it's the only time that you see X and Z together. A little better? Okay, good questions. Yes, and in chapter 2, I actually go all the way up through a four-way interaction, just to show you that it's humanly possible. I know, do I get props for that or what?
That's huge.
That's-
For four-way, you have to have everything below it.
Yes, you do. No, it can be done. Like, there's just ways that you can embed language to make this less painful, and it's not more positive, less positive. It's focusing on like, age is bad for you. Like, age is worse for you if you're a woman. The extent to which being a woman makes aging worse is even worse if you're high in grip strength. Like, you have to sort of layer your language like this, and it can be tricky, but it can be done. So, anywho. All right, 308. Let's call it a day, shall we? Let's call it a week. Let us know if you need anything. We'll be back Tuesday and Thursday for our last week of classes.
Wow.
I know, end of an era. Have great weekends. Thanks for being here. Bye. Bye, Zoomers. Bye, Roomers.